Hi, my name is Dan Bitson.
My name is Race G.
I'm Nathan Gunner.
And we're going to talk about our solar-powered TrackR tag, which is our device for senior design.
We're doing this work for a company out in Santa Barbara, California called PhoneHalo. They have an existing tag that they basically wanted us to improve. The current tag has about a 1-year lifespan, and they need to replace the device or the batteries, depends on which device. They have a couple of them. What they wanted it to last longer. They thought this was unacceptable. A lot of people wouldn't want to pay $40 for a device that's just going to fail in a year anyway. So they came to us to make it solar powered, and the idea is that it would expand the lifespan to about 5 years.
So before we started, we did some research into previous work done on a similar product. We found specifically 3 different products. We saw there's a lot of different work into it. There's the ProTag Elite, the Tile, and the Kensington TrackR. All of these very similarly would die in 6 months to a year. You need to actually buy a whole new device for it, which comes back to the main reason why we needed to make PhoneHalo's device solar powered.
So we get to meet our client with a company named PhoneHalo, and also the research part Sensi, and we got our requirements down. Basically, they just want us for the consistent battery charging, consistent battery charging over the 5-year lives, and also they wanna add. We keep the price on the $10, so they can have a better market price, and it will be doable and do not drop with the functionality they already have, like finding the device and the alarm, those kind of thing, and it should be really small from a lot of reasons, just because it's a tag that attached to a lot of things. So they ask us to do it really small, and we also have a 5-year lifespan, and optionally we proposed actually that we can have a app that actually could read the solar power panel.
This is one of our initial designs. It came up early last semester. So basically, this one uses a PIC for overcharging protection, and then a diode to make sure there's no reverse current leaking from our battery. This is our solar panel on this side. We would get typically in sunlight between 4 and 5 volts from that. So our idea here was that we would run through a very small resistor just to get the maximum amount of current out that we want. Use the PIC to read the channel from the battery, so if the battery got above 3 volts, then we would ground this through a transistor. Without the diode, then keeps it from discharging the battery. And that was kind of the idea here. It didn't quite work like we wanted to. So, we had several issues with this. First of all, the 5 ohm resistor was not enough. The solar panels don't function like a normal power source. Instead, if they're trying to drive too much current out, then the voltage just drops. So that was an issue for us. We had to change that in our next design. The microcontroller, using something like a PIC, well, it would have been a Nordic chip that's already on the device for that, is unreliable, uses a lot more power, and especially using that NPN transistor was inefficient in charging. So instead, we would switch to a MOSFET if we were going to use an active. We wound up eventually actually just going for a more passive approach to the overcharge protection.
So this is our second revision of the design. We decided to use a buck boost converter, an LM2623, in order to boost our solar voltage up. So we could only use one panel and greatly reduce our cost, as the solar panels are definitely the most expensive part that we're adding onto this design. It would also allow for a lot better charging in low light indoors. We were having a few issues with that. This would definitely help that out a lot. But the design actually didn't work just because the solar panels did not have enough current to drive that buck boost converter, so we would end up just getting nothing out of it every time because of that high switching at 200 kilohertz there.
So in keeping with our passive voltage overcharging protection, we wound up going with a regulator. This regulator keeps it at 3.3 volts, our input from our solar panels. So it'll function somewhat up to that. You need above about 2.5 volts in order to charge from the panels, but anything above 3 volts then that comes out of the panels will just get capped out. which is what we'd like. Looking at the data sheets for our battery from Panasonic, it actually starts to deteriorate if you get above about 3 milliamps charging. So we wanted to kind of clamp that down. We get a 200 ohm resistor to make sure we get enough voltage out of our panels, and then that also kind of caps out our current that we're using to charge the battery. And then again, the diode here is just for stopping leakage from occurring backward and discharging the battery when we don't want it to. And we chose a Schottky diode here because it has a very low forward voltage drop, so we're not wasting any energy there, at least not much.
Yeah, so this is a basic block diagram of our final design. So we have the solar power here. I'm going to go into a 3.2 volt regulator, or 3.3 volt I think it was. That will go into our charging circuit, which will charge that battery and go to the actual tag, which will connect over Bluetooth to the smartphone. For our actual final design, we were not able to load any firmware onto the TrackR tag, so we used a separate board. That's what you see here, in order to run our app off of, and connected that to the smartphone just to show that we could connect with our own firmware there.
So then we start to design the application on the smartphone so we can find the device. Since we don't get any Apple code from Phone Halo, we actually modified Nordic Apple iOS code for our final design. And this is just a flow chart to show how this whole process of the code works. First, it starts with when user log into the whole user phase, it's gonna ask you if you turn on the Bluetooth or not. If you haven't turned it on, then you will just directly go to the setting to turn on Bluetooth. And then it will automatically, if you connect to Bluetooth, it will automatically start searching the whole device. And if you find it, it will directly show the name of the device. So you can just click on it, go to the next page. If it doesn't find it, it will just go back and keep searching it. And when user go to the find phase, they can just simply press the find button to make the device make alarm. If they push the read voltage button, they will go to another interface, which is the read solar panel option that we have to read the voltage. And if sometimes it will have issues for the connecting, so the user can choose forget the device, so they can reconnect the whole the device again, just have a better function.
So here we have a picture of just the exterior of our final design here. It's a little bit larger than we'd like because we couldn't put everything on a single board, and I can show that here on the next slide. This is the interior. So we have our own added PCB here. That's our charging circuit in addition to Phone Halo's PCB. We would have liked to put it all on the same board, but unfortunately we didn't get information that was necessary for us to do that. So we just wound up making our own and then trying to fit it all into one box. Increased the size a little bit, but it's still a fairly small size like it was meant to be in the requirements.
So now we're just going to talk about a little bit of problems that we encountered on this project. The main issue that we had was actually with our client Phone Halo. We did not receive any schematics, code, or firmware from them after asking several times. This made it very difficult for us. As you saw, we couldn't put everything on the same board. We weren't able to edit firmware without a separate board. And we ended up having to just basically rebuild it using Nordic's provided code that they gave us. Another problem we ran into was the USB board on that evaluation board, that separate board we had, was broken, so that made it very difficult for us to do firmware updates, actually impossible until we were able to repair that. Also, the solar panels didn't handle the switching well. What I mean by that is we weren't able to use that buck boost converter. It took us a while to figure out exactly what was going on with that. We designed a lot around that before realizing that that wasn't a viable option.
So here we have costs to manufacture each individual device. So we have prices for the parts that we used in bulk, typically from DigiKey if you buy them. Price for about if you're buying 1,000 at a time. As you can see, the total cost of manufacturing is about $7.45 if you assume that we're going to stick it on the same PCB that they had before, which is pretty well under the $10 threshold that we wanted to maintain. Here we have a chart of the total costs that we used when doing this project in senior design. We bought several parts and things, and then the milling we did in-house, so it didn't actually cost us anything, but we still wanted to include that because this is just a rough estimate of what the milling might cost to do somewhere else. Overall, we spent about $85, which is well below the $100 budget that we were allotted for this project.
So from this project overall, we just met Fenghelo's project requirement, which is under $10, and the device is very small and it gets solar charging. For this requirement, what we didn't, like, since we don't have a lot of information from Fenghelo, which is really necessary, like the schematic, the firmware, and the software code, we were not able to make the best device since it's not that small. And we didn't also have the radius voting from the app, but it's just actually just an optional requirement. And I think we actually complete this project fairly well since this gets solar charging, and the size and the price is meets the requirement.